Welcome to episode 11 in the Accident Theory series. In the last 10 episodes, we focused on understanding causation and the essential elements of conducting effective investigations. We also learned about root cause analysis, emphasizing the difference between immediate causes and underlying systemic issues. Key investigation techniques were demonstrated, such as interviewing witnesses, collecting evidence, and reconstructing events. The series has also covered common biases that hinder investigations, methods to avoid them, and the importance of a structured approach. The previous 10 episodes, which represent a third of the content in this series, essentially defined what an incident is and how an investigator would react to it. Moving forward, we will now use various types of models to justify our theories. In this episode, we will look at accident models and learn that all models are not made equal. We will take a look at randomness and chance as well as non-zero risk. In the upcoming episodes, we will explore some of the standard causation models used by occupational health and safety professionals. Before diving into these models, it is important to first understand what a model is. A model is a theory or abstract explanation of how a system works, how components relate, or how one thing leads to another. Simply put, it helps fill in the gaps when we have incomplete information or when we want to predict future unknowns based on present and past knowledge. Models are used in every professional discipline where tangible explanations are required for an abstract idea. From engineering to accounting or chemistry to story writing, there is probably at least one model which is used to aid in the development process, or to rationalize an abstract thought, making it easier to document in a report or present to justify a course of action. All methods and tools used for reporting, recording, and analyzing incidents are built around an incident causation model, whether consciously or unconsciously. This model influences everyone involved in the process, including the person reporting the incident, the supervisor, the investigator, and the analyst. It also affects how reviewers interpret the collected data, shaping how the incident is reported, documented, investigated, and understood. Therefore, having a clear understanding of incident causation theories and deliberately selecting an appropriate model is crucial before starting any data collection. Incident investigation models typically fall into two categories. Individual incident models organize the information collected during an investigation and are used to explain the causes of specific incidents. Since incident databases are created based on these investigations, the model selected will shape the type of data available for future reference regarding incidents and their causes. Incident models are essential for designing effective prevention programs. They help bridge gaps in our understanding when information is incomplete or when predicting future outcomes based on current knowledge. By using a model and partial data about a system, we can infer missing details. However, if the model is inaccurate, our prevention strategies may fail. These models also influence how we gather data to explain individual incidents. When comparing an incident model to something tangible in the real world, it is not a scientific formula or a recipe in the kitchen. An incident model is not a step-by-step guide on how to complete an investigation. Rather, it is more akin to a map used for navigation. Just like a map helps a lost traveler find their way when they are missing key details about a location, an incident model helps fill in the gaps when an investigator does not have all the information about an incident. If the map is accurate, it can be easy to reach a destination efficiently, just as a well-designed incident model allows for the understanding of the causes of an incident and allows for the design of effective prevention strategies. However, if the map is outdated or incorrect, it is easy to get lost, just as a flawed incident model can lead to ineffective or misguided safety measures, potentially allowing similar incidents to happen again. Incidents occur wherever there is an opportunity for them to happen, meaning they take place where risk factors are present. These risk factors create the conditions that make an event possible. When an incident happens due to these underlying conditions, we often attribute it to chance. In such cases, we may describe the event as occurring randomly, though in reality, it is the result of specific factors aligning. The presence of these risk factors increases the likelihood of an incident, even if the exact timing or details of the event cannot be predicted with certainty. Understanding this relationship between risk factors and incidents is crucial for identifying potential hazards and preventing future occurrences. In simple terms, randomness is not knowing the time that an outcome could occur, and the outcome cannot be predicted with certainty until it actually occurs. Randomness and chance are closely related, as both refer to the unpredictability and uncertainty of events. Randomness describes situations where the outcome is unpredictable and lacks any specific pattern or order, such as rolling a die or flipping a coin. Chance, similarly, refers to the likelihood of an event happening without any deliberate control or influence. Depending on opinion, casino games can be considered games of chance, randomness, or probability, depending on how you look at it. Both concepts emphasize that outcomes are not predetermined or influenced by prior events, and they involve uncertainty. However, while randomness often refers to the unpredictability of specific results, chance typically emphasizes the possibility or likelihood of those results occurring. In essence, randomness is the state of unpredictability, and chance reflects the opportunity or likelihood for any of those random outcomes to happen. Randomness relates to the timing of an event, not its causation. Phrases like "accidents don't happen, they are caused" are commonly used in safety programs. The idea behind such slogans is that if something has a cause, it is not truly an accident. However, an event can be both random and have causes at the same time. While the exact timing of the event may be random, the causes, such as physical conditions or human behaviors, are factors that increase the likelihood of the incident happening. In other words, randomness does not eliminate the presence of underlying causes. The best way to visualize that an event can be both random and have causes at the same time is to unfortunately dip our toes into statistical analyses, mainly the study of probability and how it relates to randomness and chance. Randomness, chance, and probability are all concepts that deal with uncertainty. If we were to flip a coin and view it as a random event, we cannot predict whether the coin will land on heads or tails in any single flip. Probability, on the other hand, provides a way to measure and quantify the likelihood of these outcomes over time. While each flip of the coin is random, probability tells us that there is a 50% chance of landing on heads and a 50% chance of landing on tails. In essence, probability is the mathematical tool we use to understand and express the likelihood of outcomes within random events. People or machines may experience incidents more often than others, but the incidents themselves are inherently random. For example, in motor vehicle crashes, we see recurring patterns such as age, gender, intoxication, along with environmental factors like late-night driving and specific road conditions. However, while factors like age, gender, intoxication, and speed can increase the likelihood of an incident occurring, they do not guarantee it. This is different from how the height from which a rock is dropped and gravitational pull determine the time it takes to fall, as those are predictable and constant, whereas incidents are not. Even with the identification of more risk factors and risky scenarios, we cannot predict incidents with certainty. For instance, not every young, male, or intoxicated driver will crash, despite the increased likelihood. The fatal outcome remains a matter of chance for each individual driver. While reducing or eliminating known risk factors can lower the probability of an incident, there may still be unknown factors that influence the outcome. Thus, complete prevention may not be immediately possible. Addressing known causes depends on decision-makers' willingness to act, aiming to reduce the chance of outcomes that are possible but not guaranteed. Did you know? The concept of randomness and probability was significantly advanced by the 17th century French mathematician Blaise Pascal. His work on probability theory emerged from his correspondence with Pierre de Fermat about gambling problems. Non-zero risk refers to the concept that there is a measurable probability, greater than zero, that an undesirable event could occur. This means that while the chance of the event happening might be very low, it is still possible. For example, if a certain risk has a 1% probability of occurring, this represents a non-zero risk because despite the low likelihood, there remains a chance, however minimal, that the event could actually take place. Understanding and acknowledging non-zero risk is crucial in risk management and decision-making processes. It allows individuals and organizations to prepare for and mitigate potential uncertainties by considering even unlikely scenarios. By incorporating non-zero risks into their planning and strategies, decision-makers can better manage potential impacts and make more informed choices rather than assuming that low probabilities mean no risk at all. This approach ensures a more comprehensive assessment of risks, leading to more effective prevention and response strategies. When we encounter a hazard, we recognize that there is a potential for adverse outcomes. The term accidents waiting to happen is often used to emphasize the danger. While many hazards pose only a negligible risk, there are also issues we might overlook, such as design flaws. Donald A. Norman from the Design Lab at the University of California, San Diego, argues that many errors are often unavoidable due to poor design, referring to these as design errors. Examples include faucet knobs that are installed backwards, doors that are designed to be pulled but look like they should be pushed, machinery that forces poor operator posture, and shifts that require workers to maintain vigilance for excessively long periods. Such errors occur when the design of equipment, tools, or environments leads people to make mistakes. People often think that the risk of an adverse outcome decreases with each successful completion of a task. However, the activity might involve inherent mismatches due to poor design in equipment, workspace, or procedures. For instance, if someone repeatedly uses an unsuitable ladder to install holiday lights and succeeds each time, they might start to believe that the risk associated with the incorrect equipment is minimal. Despite their low failure rate, any occasional mishap is viewed as a surprise or personal failure rather than a predictable result of the design flaw. Adverse outcomes may be unexpected but are not necessarily unpredictable. Many design flaws in industrial systems are well known, even if they are not recognized by the designers, managers, or operators involved. Simply being aware of a hazard is not enough to eliminate it. Individuals may be indifferent, careless, or believe it is not their responsibility to address the hazard. People might acknowledge that a certain outcome is possible, but either underestimate its likelihood or misunderstand how probability works. When evaluating risk elimination, it may be deemed cost-ineffective based on some cost-benefit analyses. This leads to what is called acceptable risk, meaning that while the risk is acknowledged, it is considered acceptable by decision-makers. Often, those making these decisions are not the ones directly exposed to the risk, which creates controversy over using cost-benefit analysis in safety decisions. As long as there are non-zero risks in a system, incidents will eventually happen, even if the risk is minimal. Statisticians refer to such occurrences as rare events. Acknowledging that incidents are inevitable does not mean accepting them as unavoidable or unpreventable. It simply reflects the probabilistic nature of non-zero risk. This principle is controversial as public agencies strive for zero incidents. Authoritative sources acknowledge that zero risk is unattainable. The goal for occupational health and safety professionals is to minimize risk as much as possible. Ironically, the most effective approach is to recognize that incidents arise from both normal and abnormal factors inherent in the system, even if the outcomes themselves are not inevitable. Look at the holiday image on your screen. How many unsafe activities do you see? Would you consider any of these activities to be non-zero risk? You may want to pause the episode and, after taking a good look, share your thoughts in this episode's group chat or in the comment section if you are following on social media. In episode 11, we began our introduction into modeling. We first learned why we use models in incident investigation and also looked at randomness and chance. We finished the episode by defining how non-zero risk relates to investigations. The key points from episode 11 are: a model is a theory or abstract explanation of how a system works, how components relate, or how one thing leads to another. Models help fill in the gaps when we have incomplete information or when we want to predict future unknowns based on present and past knowledge. Individual incident models organize the information collected during an investigation and are used to explain the causes of specific incidents. Incident models are essential for designing effective prevention programs. They help bridge gaps in our understanding when information is incomplete or when predicting future outcomes based on current knowledge. Incidents occur wherever there is an opportunity for them to happen, meaning they take place where risk factors are present. Randomness describes situations where the outcome is unpredictable and lacks any specific pattern or order, such as rolling a die or flipping a coin. Chance, similarly, refers to the likelihood of an event happening without any deliberate control or influence. Non-zero risk refers to the concept that there is a measurable probability, greater than zero, that an undesirable event could occur. This means that while the chance of the event happening might be very low, it is still possible. When evaluating risk elimination, it may be deemed cost-ineffective based on some cost-benefit analyses. This leads to what is called acceptable risk, meaning that while the risk is acknowledged, it is considered acceptable by decision-makers. COHSI provides its students with a multiple-choice quiz at the end of each episode, which can be used as practice material for the content that has been covered. A free version of the quiz can be accessed by anyone following our content on social media by using the QR code shown on the screen. If you are a COHSI student, please complete the discussion board topics found throughout this unit, as well as the episode quiz. Both of these tasks can be found under their appropriate tabs in your learning portal. If you have any questions or concerns, please reach out to your course instructor. Thank you for watching and have a safe day.